Here we're told we have a rigid insulated tank right here that's initially evacuated, and it's connected through a valve to a supply line that carries steam at 1 megapascal and 300 degrees C. The valve's opened and steam's allowed to flow slowly into the tank until the pressure reaches 1 megapascal. There'll be steam flowing here until the pressures equalize. It's the pressure that pushes the steam into the tank. So once the pressure's equalized, there's no more steam that goes into the tank. And we're asked to find the final temperature of steam in this tank. So this is going to be a first law analysis problem. The reason I think that is because we're trying to find a final temperature. So that is related to internal energy, which makes me think of the first law. And I'm going to apply that first law to the tank because I'm trying to find the steam, the temperature of the steam in the tank. So I'm going to go ahead and draw a control volume around the tank. Actually, it's probably more appropriate to put the control volume on the inside just because it's the steam only that I'm interested in. I'm not concerned about the tank material. Okay, so that's the control volume I'm going to use, and I'm going to write out the first law. I'm going to write out the rate form, but then I'm going to integrate that in time to get a before and after form. You'll see what I'm talking about in just a moment. So we'll write out the full form of the first law. Okay, so there we go. And what I'm going to do is, if you look at this equation, you'll see that it gives us the rate form. This is the rate at which the total energy inside the control volume changes with time. This is the rate of heat transfer, the rate at which work is being done. And in this problem, I'm not really interested in the rates of what's going on here. What I'm interested in is a before and after situation. I want to just know the final temperature, so I'm curious about the after situation. So I don't care about the rate. I just want to look at the before and after. So to do that, what I'm going to do is integrate that entire equation with respect to time. And when I do that, the dE dt term integrated with respect to time will just give us a delta E in the control volume. The rate of heat transfer just becomes the total amount of heat transfer into the control volume. The rate at which we do work will just be the work. When we integrate this, the rate at which total enthalpy is coming into the control volume, that will just be the total enthalpy coming into the control volume. The total enthalpy. So it'll look like this. One of the assumptions in doing this time integration here is that these properties aren't changing with time, that they're essentially constant with time as the stuff comes in, which is okay in this problem because the steam, this is assumed to be like a big reservoir of steam. It's in a pipeline. So as this fills up, it's always coming in at 1 megapascal and always coming in at 300 degrees C. So these properties just stay constant with time. And then, of course, we have the same thing. Let's clean that up. At the outlet, at any outlets that there might be. And when we did this time integration, this is just the mass. It goes from being the mass flow rate to just the amount of mass that's coming in. Okay, so that's what we get when we integrate with that first law with respect to time. It gives us now a before and after. The change in total energy within the control volume, that'll be equal to the change in internal energy plus the change in kinetic energy plus the change in potential energy inside the control volume. Now, the initial properties inside this tank are zero. It's initially empty, so there's no mass inside there. So the initial kinetic energy and potential energy is just zero. And then the final kinetic energy, it's all going to be stationary in here, so there is no, macroscopic velocity. So the final kinetic energy is zero. The potential energy, if we just put a reference point right at the middle, that'll just be zero. So these terms will be zero. There is no change in kinetic and potential energy. Similarly, I'm going to assume that the kinetic energy and potential energy coming into the control volume is not a factor, that the specific enthalpy really dominates the flow coming in. So I'm assuming these quantities are small compared to the specific enthalpy, which is probably a pretty good assumption as long as this pipeline isn't if the cross-sectional area of this is microscopically small, then it's possible these could be significant, the velocity in particular, but we're not going to assume that that's the case. Now, as far as the mass flow rate going out, or the mass going out, there is no outlet in this tank, so that term is just 0 because there are no outlets. So we don't even have to worry about that. The heat transfer into the control volume is going to be 0 because it's insulated. So we're going to assume that there is no heat transfer, so that's 0. And the work done by the control volume on the surroundings is 0 because there is no rotating shaft. It's a rigid tank, so there's no PDV work. There are no springs, no electricity, that sort of thing. So that's 0. So when we simplify this, we're going to have the change in internal energy inside the control volume is equal to the mass coming in times the specific enthalpy coming in. Right? The inlet is right here. Okay, so we now need to, and let me go ahead and expand out the internal energy. The internal energy in the control volume will be the final mass in the control volume times the final specific internal energy in the control volume minus the initial mass in the control volume times the specific internal energy within the control volume initially. And of course, the initial mass inside the control volume is 0, so that whole quantity is 0. So let me write it one last time. The final mass inside the control volume times the specific internal energy in the control volume once it's filled is equal to the mass that's come in times the specific enthalpy that's come in. So that's what we get from the first law applied to that control volume. Now to find the mass quantities, the final mass in the control volume and the mass coming in, we can apply the conservation of mass to the same control volume. And I'm going to do the same thing like I did to the first law. I'm going to start with the rate form, and then I'll just integrate that whole thing in time to give me a before and after. And what that comes out to be is the change in mass in the control volume is equal to the total mass coming in minus the total mass going out. Again, there is no mass going out, so that's 0. The mass coming in, we're just calling m in. The change in mass within the control volume would be the final mass in the control volume minus the initial mass in the control volume. But the initial mass in the control volume is 0 because it's initially evacuated. So we see that the final mass in the control volume is equal to the mass coming in. So we can make use of this up in this equation, and you'll see that we can divide through by the masses. So we're left with the final specific internal energy within the control volume is equal to the specific enthalpy coming in. So that's ultimately the relationship we have here. So to determine the specific enthalpy coming in we can find because we know the properties of what's coming in. Right? We know it's at 1 megapascal, 300 degrees C, and we know we're dealing with superheated vapor water since it's steam. So let's go ahead and write that out. So using a superheated vapor table for water, and we'll get this specific enthalpy coming in. Turns out to be, let's see, it's 3,051.2 kilojoules per kilogram, and that's for a pressure of 1 megapascal and a temperature coming in of 300 degrees C. By the way, so I looked that up from a table. I used the table from Moran et al. From Wiley. So that's the table I used to get this. Okay, so now I know that the final specific internal energy within the control volume is equal to 3,051.2 kilojoules per kilogram. And I also know that it's given that the final pressure within the control volume is also 1 megapascal. Again, it's because it's being filled up until the pressures equalize. So now I have the two properties at the final state within the control volume. So I can go back to the property tables and find the corresponding temperature for this. Okay, so if I go back to the property tables and find the corresponding temperature, it'll come out to be 456.2 degrees C after you do a little bit of interpolation. Right, so that's, and then this, by the way, is from the superheated vapor tables. You'll find that for this combination of properties that we're in a superheated vapor phase, and the corresponding temperature for that specific internal energy at that pressure is 456 degrees Celsius. So there we go. That's what we were asked to find. So just a couple of things to highlight in reviewing this problem is, first of all, this is a transient problem. It's not a steady state. It's transient because initially this tank is empty and then it fills up. So it's changing with time. So that means it's transient. We applied the first law to this control volume, and we applied the form of the first law using sort of the before and after expression, right? And we simplified this knowing that the tank is well insulated, it's rigid, kinetic and potential energy effects are negligible, there is no outlet, and then we also know that the initial mass in the container is 0, so that simplifies things a little bit here. We applied conservation of mass to that same control volume to find that the final mass inside the control volume is equal to the mass that we let in. That makes sense because it's initially evacuated. Whatever mass that we let in is going to be the final mass inside the control volume. So we arrived at this expression from the first law combined with conservation of mass. And then we made use of property tables ultimately to find the final temperature in the control volume. All right, we'll end the example there.